Okay, so in this video, we will be covering the structure-activity relationships of our benzodiazepines. So here is the summary of our structure-activity relationships. You can refer to this after you have gone through the video, or if you want, you take a screenshot for this is the general SARs. Before we move on, let's talk about the different parts of our benzodiazepine. So our benzodiazepine is made out of three rings, primarily A, B, and C, which is separated from B as opposed to ring A, which is directly connected or fused with ring B. So the numbering system starts with nitrogen going towards the carbonyl group. So that's number 2, number 3, number 4 is nitrogen. At number 5, it is where ring C is bonded to. Please take note that 6 is this atom right here. This is not counted. These two atoms are not counted because they are fully bonded carbons, and you cannot bond new things to them anyway. Okay, so 7, 8, 9, there's no 10. And for ring C, since it is separated from the fused ring AB, it is numbered differently. It's 1 to 6, but this time it has a prime on it. 1 prime, 2 prime, 3 prime, etc. Okay, so that is the ring and the numbering system. Let's go through each SAR now. Okay, so this is the general structure of our benzodiazepines. So in general, electron attractive substituents on ring A enforce activity. In particular, something that is bonded to position 7 enforce activity. Ring B is necessary for activity, meaning you can't change the substituents on B too much. And for ring C, the electron attractive substituents with small volumes on benzene ring of C5 can enforce activity as well. So let's go through it ring by ring. So on ring A, so this is ring A. So let's number it 6, 7, 8, 9. So if an electronegative group is substituted at the 7th position we're going to talk about here, electronegative group meaning it has a high electronegativity like our halogens, there is increased activity on and binding activity, meaning your benzodiazepine, if it has an electronegative group attached to it at the 7th position, it makes it more potent. And there is actually a hierarchy on potency. Okay. Next SAR is substitution at 6, 8, and 9 decrease activity. Meaning if you substitute any at these positions, you actually have less activity as compared to not touching them at all. And if ring A is a heterocyclic ring, meaning it's not a benzene ring, it has a weaker activity and affinity compared to an aromatic ring. So in this case, a benzene ring is superior to our cyclohexane. Okay, so those are the SARs for ring A. For ring B, we're gonna talk about this ring now. A proton accepting group at the 2 position here, like a carbonyl, is necessary to interact with the histidine receptor residue. So you are not allowed to change this substituent at ring number 2. Otherwise, you will have problems with binding. This is mandatory, needed. The next one is substitution at the 3 position with a hydroxyl group has comparable potency to non-substituted analogs but are excreted faster. Meaning, if you compare those with OH and those without OH, they have the same activity. However, those with OH are excreted faster, meaning they have shorter half-lives. However, this has a benefit of being rapid terminating benzodiazepines. So if you have OH, it is useful for inducing sleep or just to start as a sleep aid. Okay? And substitution at the 3 position with alkyl substituents, meaning long chains like methyl or ethyl, decrease activity. So if you want to substitute at 3, preferably the only one allowed is OH. It doesn't affect activity, but it increases elimination rate. If you substitute an alkyl group like ethyl or methyl, it decreases potency or it decreases activity. So in this case, this is an example of 2 drugs which has an OH difference. So they're practically the same drug. However, they have a difference in the 3rd position in which oxazepam, this is oxazepam, has an OH while diazepam on the right has no OH. The T1 half or the half-life of oxazepam is actually 8.2 hours. So it's a quarter of a day. Well, the T1 half or the half-life of diazepam is around 2 to 5 days. So as you can see, this the difference between those two is significant. Oxazepam has a shorter half-life, therefore it lasts shorter as compared to diazepam. And that is only with the difference of our hydroxyl group. On ring C, the 5-phenyl ring C, it's called 5-phenyl because it bonds at position 5, is not required for binding. However, this aromatic ring contributes favorably to steric reactions to receptor binding. Substitution at 4 or para is unfavorable, meaning it lessens activity. However, substitution at 2 is not detrimental to agonist activity. It doesn't mean it is better, it just means it has no negative effect. You can bind something to 2 if you want to alter its physicochemical properties, and you will not alter its pharmacologic potency. Next is you can also have fused rings on B. So if you remember the numbering, it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So annihilating the bond between 1 and 2 with an electron-rich ring such as a triazole, this is a triazole, or an imidazole, results in pharmacologically active benzodiazepine derivatives with high affinity to the receptors. So this is actually allowed, and these actually are potent drugs. So this is a triazole and this is an imidazole. And here are some examples of benzodiazepines that have this annihilated ring on 1 and 3. So you have alprazolam, triazolam, and midazolam. And that is all the related structure activity relationships for our benzodiazepines. I hope you have learned something from this video and see you on the next part of our SAR videos. Thank you and goodbye.